Good morning and welcome to Scientists and Explorers Live. My name's Jamie from Encounter EDU, and it's wonderful to have you all with us. So many homeschool students from around the world, and I wonder if any of you are still at school. I know there are some classes still happening. Now we have students from India, Bermuda, USA, UK, Malaysia, and Ukraine on this morning. So good morning to everybody taking part. I'm just going to check on the live chat to see if we have any shout outs. We have Oscar, we have Rafaela, we have Ernie. Great to have you all. Wonderful to have you with us. And it's going to be just a fantastic live lesson. Why water is weird. Now, I've had a look at what's coming up and the description of the talk, and I really thought there are only three types of water. I think it's, if I'm in the Arctic, it can be frozen. If I'm on the coral reef, it can be a bit like this. And if I'm making a cup of tea, there might be some steam around. But we'll find out that probably water is a lot weirder than that. Before we get going, a few points to make. Now, we've got a live chat running, and that's running beside the video. So please do post any questions or comments you have. Now, because it's using YouTube, that should really be done by an adult, parent, care, mum, dad, whoever might be using that. A teacher maybe still operating that for you. Please do try and keep the comments and questions on point. It is a live classroom. And so let's try and observe similar classroom rules. And then just to let you know that the live chat will take place, a Q&A session after the talks. We've got a great presentation coming up from Phil, and we'll join him shortly. But we've got that section for about 15, 20 minutes of presentation, and then we'll get onto the live chat afterwards. If you are having any technical issues or you can't use the live chat, do remember that there is a chat function on the Encounter EDU website, and there's a small speech bubble in the bottom right-hand corner. Just click on that and you'll be able to talk with one of the Encounter EDU team who will be able to help you with any inquiries you have. But without further ado, I'm going to see if we can get Phil on the line. Phil, good morning.
Good morning.
How are you?
I'm very well, thanks.
Fantastic. And thank you so much for being part of Scientists and Explorers Live. We've got this fantastic session to why water is weird. So I'll pass over to you.
Okay, thanks very much, Jamie. Sadly, unlike Jamie, I couldn't get a watery background, so you'll have to forgive me for that. But let me tell you a little bit. I just want to say a little bit about who I am, what I do. I'm a science writer, so I write books and articles, magazine articles, articles for newspapers about science. And one of the books I wrote was about water. And I began my career in writing as a science editor. So I worked for a famous science journal called Nature. And just after I joined Nature, they published a very weird paper. It was about water. And here it is. I've got a slide of it here. So it has this complicated title. Don't worry about that. It all sounds very sort of technical and scientific. But basically what they were reporting was something very odd. They said that they had a solution that had biological molecules in it, protein molecules that did something to cells. And then they just kept diluting it. They kept adding water to it. And what they found, you'd expect in that case that the whatever it was that those proteins did would sort of gradually go away as it got more and more and more dilute, just like, the taste of a drink will go away if you keep diluting it with water. But that didn't happen. What they saw instead, this is a graph of what they showed, and it's just measuring the biological activity, that whether these proteins were doing anything or not. And you see that as it got more and more dilute, that behavior didn't go away. It kept coming back. And the dilution here, by the time you've got to 60 on this graph, it is so dilute there should be essentially no proteins left in there at all, and yet it's still doing what they do. So what's going on? Well, they didn't know. Nobody really knew, but they had a strange explanation that they put in the paper. And this is what they said. They thought water, they said, could act as a template for the molecule, these protein molecules. For example, by an infinite hydrogen bonded network or electric and magnetic fields. What does that mean? Well, that's what I'm going to talk about. Now, the thing about this paper is that this work was never reproduced. It was never proved. And in fact, most people, pretty much everyone now, thinks that the paper was wrong. There was something weird going on here, but we don't know what it was. But what was striking about it was that these researchers seem to have found a way of using the weirdness of water to give some kind of plausible explanation for this strange thing that they claimed they were seeing. And it seems that water has this property of attracting weird scientific claims. It gets even weirder with this one. When I was writing a book on water, people would say to me, "Oh, have you heard about the work of this guy called Masaru Emoto? He does incredible things with water." And this is one of the things that was reported in his book, or claimed in his book. So he said that some researchers took out some water from a dam in Japan and they froze it, and it just looked like this kind of black, shapeless kind of stuff. Then they got a Buddhist priest to pray by the side of the dam for an hour, and then they took out some more water and they crystallized that, and it looked like this. Now, I don't know that I believe these claims. These look very, very peculiar. If these are like snowflakes, they're like no snowflakes I've ever seen. So I haven't the faintest idea what's going on here. But this is just another example of the weird claims that water seems to attract. Now, when I joined the science journal Nature, I had just finished doing a PhD, a doctorate in physics, and that just happened to be a doctorate studying the physics of liquids, what liquids were like. The weird thing was that I never studied water throughout all of that PhD. People said, "Don't look at water, it's too strange. It breaks all the rules. It breaks all the usual rules that liquids follow." So I studied things that no one really ever encounters, like liquid argon and liquid nitrogen, which are normal liquids. They behave as physicists want them to, but water doesn't. Now, why is that? That's really what I want to talk about. And let's start by looking at what water is like. And you are probably familiar with the idea that water is a molecule called H2O. And all that means is that it's made up of an oxygen atom. So in this diagram here, the red ball is the oxygen atom and two hydrogen atoms stuck to it. These are the white balls. Okay, and it looks simple enough. It has this kind of bent shape. But you can tell right away that there's something unusual about this compound compared to ones like it. What I mean by that is, let's just have a look. This is, in essence, this is chemically, this is the hydride of oxygen. It's the compound that oxygen forms with hydrogen. So let's go to the area that oxygen occupies in the periodic table and just look at the hydrides of the other elements around it. These are elements like carbon and nitrogen and fluorine and chlorine. Okay, so the hydrides that they form are things like this: methane, ammonia, hydrogen sulfide, hydrogen fluoride. All of these molecules at everyday conditions of temperature and pressure are gases. But water isn't. Water's a liquid. So straight away, you can see that there seems to be something about the water molecule that is keeping them together in ways that these other hydrides don't. What's that about? Well, there are other oddities about water too. And one of the most familiar, in fact, it might be so familiar that we don't really think about it. If you have a drink, a glass of water or a Sprite or something, and you have ice added to it, the ice floats. Ice floats. Icebergs float. And because icebergs float, that was the problem that the Titanic ran into, of course. That's actually very strange, because most things, when they freeze, they get denser. And so the solid will sink to the bottom of the liquid. But that doesn't happen with water. Why not? There's something even odder about water, because even before it freezes, it starts to get denser as you cool it down. Most things, as you cool them down, they get denser. But then with water, something strange happens. When you get to 4 degrees above freezing, that's the densest it gets. And if you cool it even further than that, it starts to expand again. And then when you get to freezing point, you get this big expansion as it grows into ice. So what is going on there? That's actually a very important kind of behavior, because what it means is that the densest water in, let's say, a lake in the middle of winter, the densest water, the stuff that sinks to the bottom, isn't the coldest. It's actually 4 degrees above freezing. And what that means is that the lake isn't going to freeze solid. It isn't going to freeze from the bottom up. It's going to freeze from the top down. And so you get this layer of ice over the lake. And that acts as a kind of insulation that stops the rest of the water from freezing. And that's really important, because if lakes froze during winter, then any of the aquatic life, any of the animals that live in there would, of course, die. So instead, lakes have this layer of ice on top that keeps the rest of the lake underneath liquid through the winter. So that's really important for lake ecosystems. All of these are some examples of a whole list of what people call anomalies in water, ways in which water differs from regular liquids. And the fortunate thing is that all of them can more or less be explained by a single thing that water does, that water molecules do, and that is that they form a special kind of bond called a hydrogen bond. And so here's how it works. The water molecules, I've drawn them, on the left here. They're just this ball and stick. But actually, what they also have is a kind of cloud of electrons, of negative charge. The electrons are the things that stick atoms together. They're the things that make chemical bonds. And some of them, oxygen has some kind of leftover that it's not using in bonding, and they stick out the back. And they stick out the back in 2 kind of lobes, a bit like rabbit ears, that are called lone pairs. So out the back of this molecule, there are these areas of negative charge that then attract the hydrogen atoms of another molecule. Because the thing about oxygen is it tends to draw electrons to it, and it leaves the hydrogen atoms with a few fewer electrons. And so they have a slight positive charge. So you have hydrogen atoms with a slight positive charge, and these lobes of electrons sticking out the back of an oxygen with a negative charge, and those 2 attract each other. And that's basically what a hydrogen bond is. So it's this sort of extra stickiness. Now, water molecules aren't the only molecules that form hydrogen bonds. In fact, some of those other hydrides that I showed you earlier, like hydrogen fluoride and ammonia, they can do it too. But they can only form a few. The thing about water molecules is that it can form no fewer than 4 hydrogen bonds, 2 made by each of its hydrogen atoms to other molecules, and 2 because of each of these 2 lone pairs sticking out of the back. And so what happens in water is that the molecules join together like this. You could think of them as like this, so that you could think of the hydrogen atoms as being like a pair of hands, and the lone pairs as being like a pair of feet. And each molecule grabs onto the feet of another molecule, and they form this kind of tetrahedral arrangement. So each molecule is, or each oxygen atom is at the center of a tetrahedron, and you get this kind of arrangement appearing again and again throughout the liquid. And so you get this whole network of hydrogen bonds. And here I'm just showing a couple of different ways of representing that network. So in the bottom image here, you can see these dotted lines, these dashed lines. They're the hydrogen bonds joining the molecules together. And so the thing about this network is that it means that in order to form the hydrogen bonds, the molecules have to sort of remain at arm's length. If they come too close, then they can't really form those bonds. And so it's quite a sort of open network. There's a lot of space in between. And the key to water's oddness lies in this delicate balance that there is between the dense packing of the molecules that normally happens in liquids and this kind of slightly open network that the hydrogen bonds form. Now, in ice, that open network is rigidly imposed because all the molecules are frozen in place and they form this very orderly arrangement, okay, that essentially forms the molecules into hexagons. And these are just two different ways of representing that arrangement of what happens in ice. And you can see now that there's all this empty space in the middle of these rings. And that's why ice has a relatively low density compared to water. When ice melts, then some of these molecules can drift a little closer. And so the liquid just gets a little bit denser. So that's what happens. That's why ice is less dense than water. Now, this network in liquid water is coming and going all the time. It's these molecules are making and breaking hydrogen bonds all the time. On average, each one lasts just a trillionth of a second. That's called a picosecond. So it's very quickly rearranging. In ice, they sort of lock into place. And one consequence of this structure in ice is that actually they can lock together in many different ways. And in some structures of ice, if you squeeze ice to very, very high pressures, then some of these molecules, you can get two networks like this that interlock, and the ice is much, much denser. And in fact, there are at least 12 different forms of crystalline ice that have these different arrangements, different ways of packing the molecules in these hydrogen bonded networks. Now, here's the key to what that strange experiment that I talked about at first of where this biological activity of water kept sort of the proteins kept sort of coming back. Because what the researchers thought might be happening is that these hydrogen bonds were somehow forming a kind of mold around the protein molecules that would stay when the proteins were actually diluted away. And somehow that sort of structure of water itself would kind of have the same kind of behavior as the proteins did. Now, if you think about it, it doesn't quite make sense, because what they were making is a mold, is a negative mold, not an actual sort of reproduction of the protein shape. And in any case, like I say, the hydrogen bonds are making and breaking too quickly for that sort of structure to stay for any length of time. So the explanation didn't quite make sense. But nevertheless, that was what they put forward. But what that does perhaps lead us on to thinking about is whether water really does have some function to play, some role to play in the way biology works, in the way biological molecules work. And that's really what I want to talk mostly about in the rest of what I'm going to talk about. What happens when water is inside living cells? Is it the same as the water that comes out of your tap or not? Well, if you look at biochemistry textbooks, you could be forgiven for thinking that water just doesn't feature anywhere at all. It's just not important. If you look at a picture of a protein, let's say in a biochemical textbook, you get a picture like this, and this shows a very complicated arrangement of the chain that proteins are made of. Okay, and it shows that it folds up in a very particular way. Well, this is what we pretend things look like, as though these proteins are sort of floating around in just a vacuum. Actually, they're floating around in water. And what it really looks like is this. And you can see that this is really messy. This is really complicated. So that's a problem. It's no wonder that we don't want to think about the water. But the water is there, and it's doing some really important things. And it becomes clear that that's going to be important if we look at what the actual environment inside a living cell will look like. And here's a scale drawing of what it looks like. So here are all these biological molecules, most of them proteins. You can maybe see a bit of DNA, this kind of helix down the bottom. And you can see, first of all, it's really crowded. That just about all of this space is taken up by these molecules. There's not a lot of room for water in between. And there's only a few layers of water separating one molecule from another. So what happens to that water? Well, let's have a closer look at what it might be like around proteins. Here's a picture of a protein in which, this is just a typical protein. They're all these kind of, they tend to be these globby shapes in which the surface has been colored to show which bits of the surface are attractive to water, which bits are soluble in water, you could say, and which bits repel water, and so which bits are kind of oily or greasy on the surface. Those are the red bits. So the blue bits, we call them hydrophilic, those attract water. The red bits, the hydrophobic bits, they repel water. And you can see that a protein is a whole mixture of this. It's very patchy. And the white bits are kind of somewhere in between. And so water around this protein has to respond in some way to all these different bits, to decide, am I going to go there? Am I going to stay away from that bit? And that makes the water form into a particular kind of structure around the protein. And these different patches are actually very important for the way proteins operate, because it turns out that the red bits, the bits that repel water, they tend to stick together. And sometimes proteins themselves stick together into big kind of assemblies by sticking together the red bits that repel water. And here are just some of the complicated structures that different proteins form. One of them, actually, this one on the left, is a virus. But some of these other ones form inside our cells. And one of the main things that is sticking these different bits of protein together to form these units that actually do very important tasks within cells is the fact that those bits repel water and those patches become sticky and stick together. So this is a really important role that water is playing by either its presence or its absence. Water surrounding proteins also makes them a bit flexible, because here we've shown them as just as if they're very sort of rigid shapes, but actually proteins, to do their job, they have to be a bit flexible. Most proteins are enzymes, which are catalysts. They help biochemical reactions to take place in cells, and to do that they often have to bind to something and then chemically transform it, and that binding is a very sort of active thing. It means that the proteins have to sort of shape themselves around it, and the water around it is really important for how that works. But the water goes beyond that as well, because when protein enzymes do their job, they actually use water almost as kind of snap-on tools to perform their function. And here's an example of that. And it looks very complicated, but what you're seeing here is a bit inside a protein where it's actually doing that catalysis, where it's doing the job that it does in cells. And this little network of kind of bluish purple blobs, each of those is a water molecule, and they're fixed in place. And we can use special techniques to see where they are. They stay fixed and form this rigid sort of network that it all essentially becomes part of the protein and helps it do its job. Here's another way that water can play an important role inside cells. It can form these things called water wires. So some proteins have kind of channels or pores that thread through them, and water can get into them, and inside it can form a chain of hydrogen bonded molecules like this one here. And they're called water wires, not just because they're long and thin like wires, but because they do actually conduct. But they don't conduct electricity like copper wires. They can conduct protons, hydrogen ions. Okay, and that's really important for all kinds of biochemical processes, to allow hydrogen ions to pass from one part to another. And water can act like a kind of wire, if it's threaded through these channels, to enable protons to move very fast, because the way it does that is they can hop along the chain. So actually the protons themselves don't even have to move. What happens is it's just the bonds that move. So this red arrow here is pointing to where the positive charge, the hydrogen ion, is. And just by the bonds themselves kind of flipping so that a dashed line becomes a solid one, you can see that actually what happens is that the charge, the proton, moves along this wire. Another way that these water wires can be important, we can see that happening in molecules called aquaporins. These are proteins that are kind of like filters, and we've got them in our kidneys, and they filter stuff out of the bloodstream that we don't need. And they're threaded through by a channel of water molecules. You can see these blue water molecules threading through the aquaporin, and that allows some things to get through. It allows water to get through, but it doesn't allow other molecules to get through. And now people are getting very interested in whether aquaporins themselves, or perhaps artificial molecules that are stronger than aquaporins but also have this kind of water conducting channel through them, whether we can use them as water filters to extract salt from seawater, the technology called desalination, to make fresh water from seawater using these sorts of principles. So we can learn perhaps from biology to figure out ways of doing this. So I hope I've persuaded you that water isn't just a sort of passive backdrop to life, that it's just sort of stuff that fills cells and doesn't do anything more. It actually engages in the processes that allow life to happen. You could think of it really as a kind of biomolecule in its own right, but one that forms this very extended network of molecules that carry out these functions. That idea about what water is doing casts quite a different light, I think, on whether we believe that life could exist on other planets. You see, the search for life on other planets has tended to be based on looking for other places, other planets or moons or whatever that might have liquid water on them. And the idea is, if it's got liquid water, then we know liquid water is essential for all life on Earth. Maybe it could have it there. But once we start to think in more detail about what water is doing in our own cells, then that makes these questions a little bit more precise about, well, does it have to be water, or could other liquids do this? And we can see, I think, that there are some things that all liquids do, but there are some things that only water can do, and that it's very hard to imagine any other liquids doing. So there have been some other liquids that have been proposed for as possible solvents for extraterrestrial life on other planets, because we know that things like there's ammonia on Jupiter, there's sulfuric acid on Venus, which doesn't sound very nice to us, but maybe there's a kind of life that could exist there, perhaps. There's definitely liquid methane on Saturn's moon Titan. Could that perform some of these roles of water? Well, we can start to see that there are some things that methane just can't do that water can, because of this hydrogen bonding. So it starts to broaden our view of what sort of environments elsewhere could support life. We may be able to as well as just speculating, we may be able to answer these questions by experimentally, eventually, by going there. We've already sent spacecraft to Saturn's moon Titan. This is actually on the top, is an actual picture taken of what look like lakes. And the lower one is a sort of artist's impression of what those lakes might look like. And these are actually, as I say, lakes of liquid methane. And then there's Jupiter's moon, Europa, which has a sort of icy crust. The bottom is an actual photograph of that. But underneath that crust, we know there's a liquid ocean. And it seems to be a salty ocean of liquid water. So, that seems to be a very promising place where we might at least think some kind of life, might have started. And in both of these places, we've sent spacecraft there, but there are plans to send further spacecraft in the next several years to actually land on these surfaces and try to figure out what's there. And I think that's really exciting. And the other possibility is that we now know that there are planets that are perhaps somewhat Earth-like outside our own solar system. We know that there are, in fact, this is an old slide, and it says there are about 2,000 of these planets around other stars. We now know that there are over 4,000 of them that we've spotted, and we think they're all over the universe, really. And some of those do look a bit like Earth, but some of them look very, very different. And so we can start to ask, do we only have to look for for Earth-like planets to find places where other life might exist? Or might there be completely different sorts of environments that have other liquids where life might exist? And that, too, is a question that we might hope to answer in the next few years, because we can start now to find out what is actually on these planets, what their atmospheres are like, what sort of molecules they have on them, and perhaps even whether there's some imprint in those atmospheres of life. So let's hope that we can start to really get to grips with this question of whether life utterly requires water, or whether other sorts of life might exist that don't require water. But there's one thing that we can say for sure, and that is that every life form on this earth requires water and has reason to be thankful for the fact that water is weird. Thanks very much.
Bill, absolutely amazing. And I was thinking that we just needed water for life because we got thirsty every so often. We needed to have a bit of a drink. But it's incredible to realize, as you took this dive inside the protein molecules that help us, that water, I mean, I'm just trying to think of an enzyme, am I right in saying something like lactase, that how we digest milk products? That wouldn't work without the way that water behaves. We wouldn't be able to eat without water and these enzymes combining. Is that right?
That's exactly right. Yes, that almost all enzymes, if you take them out of water and put them into some other liquid, they don't work, or they work very, very poorly. And a lot of that seems to be because they kind of become very rigid. They don't have that flexibility anymore that water gives them. And we think that a lot of that flexibility comes from, it's almost as though the water molecules, because they're very intimately connected to the protein, they're all moving about and they sort of inject a bit of motion into the protein. And if you don't have that intimate relationship, if you just have another liquid that the protein doesn't kind of respond to, then it doesn't happen and the protein just stays rigid.
I mean, absolutely incredible. I want to get onto extraterrestrial exploration in just a bit. We had a stack of questions come through as you were talking, just about some basics around the properties of water. And this is Tom and Lottie asking why is water in most food and drink? Is that where we take it in to keep our bodies functioning?
Yes, it is. Yeah. And we need to do that, of course. I mean, you're always being told to make sure you're hydrated. And hopefully, this gives you a little impression of why that is. It's not as though, you take in the water and it just goes straight through you. That water is doing really important stuff in your cells, and the cells completely need that water. If cells get dehydrated, then all the molecules in them, find it harder to function. It seems that actually, we talked a little bit about how the enzymes need to be surrounded by water. It seems that actually they need if they fall below a certain amount of water covering their surface, there's a sort of critical threshold below which they stop working properly. So, I hope you can see now that that's why you have to make sure that you're well hydrated, because the cells are really using that water very actively to do all these processes that we need to keep ourselves healthy.
I mean, incredible. I mean, just go back to some of the physical properties of water. You're talking about the amazing bunny ear sort of system, and sort of grabbing on into this tetrahedron shape, this sort of the square sort of square-based pyramid. Mrs. Tinsdale was asking if you could just go over why it is that water is a liquid at a sort of normal temperature and pressure, but all those other ones are gases. Why isn't water a gas?
Yeah, that's it, the really crucial point. So thank you for asking me to go through that again. And the reason is that water can form so many of these hydrogen bonds. So with hydrogen fluoride, it can form hydrogen bonds. The hydrogen on one molecule of hydrogen fluoride can stick onto the fluorine of another. But that's just one bond, and that's all it can do. With ammonia, it can form more, because there are 3 hydrogens attached to a nitrogen atom. It's kind of like this, actually, like a little tripod. So it can do that. But again, it can only form kind of chains of hydrogen bonds. Only water has this structure where you get, the 2 and then the 2 and the 2 that form these tetrahedrons. And then you've got a whole 3-dimensional network of hydrogen bonds. So it's really that characteristic. It's the shape that water forms when it makes this hydrogen bonded network that makes it 3-dimensional and go throughout space, rather than just kind of chains of hydrogen bonds, which aren't going to help it keep together as a liquid.
So it's that sort of molecules attaching to one another that changes it from being a gas into a liquid.
That's right. It's the hydrogen bonds are a kind of extra stickiness. They are basically weak chemical bonds. So they're about 10 times weaker than the bonds that actually stick a hydrogen atom to an oxygen atom in a water molecule. So, those bonds stay. They're really sort of, they're really strong. The hydrogen bonds are a bit weaker, but they're strong enough to keep the molecules together for a short space of time. And then they break and the molecule goes off and finds another one. But, it's that extra sort of bonding that the hydrogen bonding gives that helps the water molecules clump together instead of drifting apart like into a gas.
Brilliant. And we've had this question a couple of times, I think from SDD Warriors as well. It's asking, does water have memory?
Well, that's exactly the question that was raised by that experiment that I talked about. First of all, in fact, this whole idea of water having memory really stems from that paper. It's, that's what it looked like, that it seemed to have this memory of the protein molecules that were in it and that had been diluted away, but the memory seemed to remain. Now, as I say, those experiments they were never repeated. No one else could find that sort of behavior, and pretty much everyone now thinks that there was something wrong about the way they were doing the experiments. It's not quite clear what it was, but there was something odd about it. So I'm afraid, sadly, although this is a lovely sort of expression, the memory of water, it doesn't seem to be a real effect. It doesn't seem to be possible for water to sort of form any kind of hydrogen bonded structure that stays for any length of time as a kind of memory of what used to be in it. These hydrogen bonds just don't last that long. They very, very quickly break up and form some other arrangement. So there's no reason at the moment to suppose that water really does have this memory of stuff that's been in it.
And if we can leave this planet for a while, and Oscar's come up with this question, which will sort of frame probably the next few, is how does water behave in outer space? Does it behave differently, or does it have to be on a planet for it to take forms that we might recognize?
Yeah, well, that's a really good question, Oscar. And the reason is that when we've been searching for places that might be a bit like Earth, and it's very, very hard to find them, and there are none in our solar system. So we think, gosh, water must be really kind of uncommon out there. Actually, water is really common in the universe, but not as a liquid. So there's a lot of water in the huge clouds of molecules, and so gas and dust, from which stars themselves form. Water is a very common molecule, and it's not surprising because actually the things that go into it are hydrogen and oxygen. Hydrogen is the most abundant element in the universe. By far, most stuff in the universe is hydrogen. That's what stars are made of. Oxygen turns out to be the third most common element in the universe. So there's loads of these atoms around, and they encounter each other and form water molecules. But in a molecular cloud, they're very, very far apart. It's very cold, and they're just gases. And so they're just individual water molecules sort of floating around. I suppose, it's possible by chance every now and again, two might encounter each other and hydrogen bond for a little bit and then probably come apart again. But there's not a lot around. But as these clouds start to sort of condense and form and form stars and then form planets, a lot of that becomes ice. And actually, water as ice, there's a lot of it about. There's, as I showed, there's the moons, not just Europa, but the other two of the other big moons of Jupiter are also covered in layers of ice, and that's water ice. There's there's water on Mars, not very much. There used to be much more, but there is some certainly frozen into the ice caps at the poles. They're mostly frozen carbon dioxide, but there's water there too. So actually, water is really common in the universe, but most of it, if it's on planets, it's usually frozen as ice, and if it's out there in space, then it's usually just lone water molecules in a gas mixed up with loads of other stuff.
You mentioned Mars there, Phil. We've got some questions about sort of Martian life. Am I right in remembering that there is evidence of liquid water or potential liquid water in some of the erosion features on the surface of Mars? And does that mean that there could have been larger forms of life on Mars that we don't know about?
Yes, the answer to both of those is yes. We certainly are pretty certain that long ago, billions of years ago, so early in its history, Mars was a watery planet, a bit like the Earth. It was warmer, and it had liquid water on its surface. There may have been even shallow seas, certainly rivers, that we can see, still sort of left as dried up riverbeds today. They look just like riverbeds on Earth, but there's no water in them. And they were carved out by running water long ago, maybe sort of 2 or 3 billion years ago, and they've just stayed ever since. So yeah, Mars did used to have liquid water, and that really does raise the question of, could there have been a form of life on Mars? And it's absolutely possible, as far as we know. We've never found any evidence for it, and it would be very hard to find, because if it was, it would be very, very simple life, bacteria really, or something like bacteria, we might imagine, that doesn't really leave fossil traces very easily. But we can find fossil evidence of very early life, bacteria type life on Earth, just by looking at the rocks on Earth, and life leaves a kind of imprint in those. And so it's possible, if we search Martian rocks, carefully enough, that we might find something like that, some evidence of life once having existed on Mars. But if it did, it seems unlikely that there's any still left. Even that's not impossible. Underneath the surface, it's possible, that there might be some kind of primitive communities of microorganisms, bacteria-type organisms still existing. But it's quite hard to see how that could really survive on the planet today, which is very cold and dry. But there's some evidence still that occasionally there are still flows of liquid water on Mars. There have been sightings from space missions that have shown features that look like they were kind of quite recently made by some kind of flow on the surface. So maybe there are still kind of frozen reservoirs of water underneath the surface that might thaw out, when the surface gets warm enough, as it sometimes does in the Martian summer, for the water to sort of burst out. It's possible. And we hope that by sending more missions to Mars, in particular rover missions, lander missions, that we might be able to find out for sure whether or not that's the case today.
So no Martian sharks?
I'm afraid I think we're pretty confident that if there was life on Mars, it would have just been this very primitive life, as it was on Earth for the first few billion years. That was all it was. Big creatures like ourselves are very, very recent in the history of the Earth, and by that stage on Mars, it had pretty much lost most of its water and had entered the sort of deep freeze that it's in now. So sadly not.
And quick question for as well, is it looking at the electrical properties of water? And can water have a charge?
Well, the water molecule does actually have a charge. And, as I said, that's what causes the hydrogen bonding. The fact that the electrons that form the bonds between the oxygen and the hydrogen, they're not evenly spread throughout the molecule. The oxygen tends to sort of gather them to itself, and that leaves less of them on the hydrogen atoms. So the hydrogens have a slightly positive electric charge and the oxygen a slightly negative one. And that's what allows the molecules to attract one another. So, there's that aspect of water having an electrical charge. Water itself is not a good conductor of electricity. But if it has any kind of dissolved salt in it, then it will conduct electricity quite well. And in fact, the fact that that any sorts of impurities make water a kind of good electrical conductor is precisely why you shouldn't remain in a swimming pool during a thunderstorm. Because if it strikes the water is conductive enough to conduct that electric charge into you.
Amazing. Very sad. We've only got time for a couple of more questions, but perhaps this one from Ludmila in Ukraine. It's a really great one towards the end. Is how much more can we find out about water and its peculiarities? Do we know everything?
Do we know everything? We certainly don't know everything. It's amazing. In fact, it still amazes me how much we don't know about water. You would think it's this, it's everywhere. We're so familiar with it. We drink it every day that surely we must understand everything about it now, but we don't. And scientists are still arguing about things that that seem quite fundamental about what is the best way to describe this complex structure that liquid water has. And in particular, what does it do when it gets close to molecules like proteins? That's still a very active area of research. We still don't really know what happens to water at the surface. Where the water molecules don't have other molecules to form all these 4 hydrogen bonds to. Right at the surface, there's nothing above it. And so what do the water molecules do there? Do they kind of reorient themselves so that they can form, as many hydrogen bonds as possible? And if so, does that change what the water is like at the surface? It probably does. But these are questions that we still don't quite understand. And in fact, there are discussions about whether water at the surface is actually slightly acidic for reasons to do with that. Or some people say, no, it's actually alkaline at the surface. And there's this big argument about which it is, which seems like a very fundamental question, but it's very hard to answer. So there's a lot that we still don't know, even at this very sort of fundamental level of what the molecules are doing. There's still a lot that we don't know about water.
That's absolutely fascinating, Phil, to know that we don't really know how the surface of water works. Thinking back to one of the diagrams we've used, I've got this image in my head now of thousands or millions of water molecules with a spare hand waving at the surface. I don't know whether that's true or not. There are a few more questions that it's very sadly we don't have time to answer, but thank you so much for this fantastic live lesson. It's been riveting, and lots of questions now still coming up around, extraterrestrial life. Will we end up like Mars in the future? All these things. So I think we've got some budding chemists, physicists, biologists, scientists for the future. But for now, it's just to say thank you so much, Phil, and thank you everybody who's been watching. Just to go through a few shout outs before we close. We've got friends of Malawi watching. We've had Liz, Freya, Stefano, Ernie, Amelia, Rohan, Phoebe, Elijah, the SDG Warriors, and Lucas and Elena in Oxfordshire. So thank you all so much. It's been great having you. For now, until tomorrow, when we have Dr. Helen Findlay on ocean acidification, and we also have a science club on coral over the next 2 weeks as well. But for now, it's thank you and bye-bye.
Thanks very much for watching. Thanks, all of you.